All right, I
Okay.
think we should be set. Yeah, so we're team 11260 Upper Creek Robotics from Longmont, Colorado. And today we'll be talking about streamlining robot evolution and just a lot of things we've learned from the Power Play season. We will be going over four main points today. Modular design and rapid prototyping. Malcolm will talk about that. Then Jack will talk about refining subsystems through iteration and revaluing tools from past year. Then Julian, will be talking about learning from your competitions. So here's Malcolm.
All right. So this year we tried as much as possible to prototype as many different designs as possible because I think the most valuable thing that you can have when you're designing a robot or when you're making new parts is data and information about how certain elements of your robot work. And that data can be, you want to get as much of that data as possible by trying out as many things as possible and as quickly as possible. And in order to do that, we have a system of rapid prototype or of modular design that is built into our robot. So we have subsystems of our robot that can be swapped out very easily from just one or two parts and a couple of bolts, and then that we're able to test out new designs very easily. And this also helps a lot when we're trying to design in parallel with our software team, because we are able to have our software team work on developing code, and then we were able to build replacement subsystems at the same time and then swap them out very quickly with minimal influence on the rest of the robot. So this is an example of some of the larger modular subsystems of our robot. So our intake subsystem was a big one. Our original intake was a very different and unique design that we weren't able to get to work, but it wasn't a problem because we were able to swap it out very easily. It can be swapped out from the wrist. There's a hex shaft that can be swapped out very easily. And then we also have a junction brace. Our junction brace is something that we've had since very early on in the season. And it's something that's gone through a lot of iterations that Jack will be talking about later, but all of those iterations were made possible because we were able to swap it out from the servo right at the top. And then everything also, our entire assembly that goes on top of the turret can be swapped out very easily from those blue 3D printed parts there. And we're able to basically rebuild the entire subsystem that's on top of the robot and swap it out and have all of our development work in parallel. So this is an example of our intake. We prototyped very early on with a rubber band type of intake where it would go over the top, stretch the rubber band,
No.
and hold the cone. And then we tried a bunch of different things to be able to make that work. We had a lid that you can see on top of the cone on the left that would stabilize it a little bit more. But in the end, that didn't work out very well. And we were able to swap it out very easily using the modular design. And we have now a claw intake that we're able to also add many things to. We have like a funnel that will hold the cones and makes intakes faster. And these are things that we're able to test and we're able to prototype, and we're able to do all of this very easily because we have this modular design. So in order to talk a bit more about the iteration and the all of the different things that we tried and the way that we're able to develop some of our subsystems, this is Jack who will be talking about that.
Iterative design works very well with modular design because iterative design involves lots of quick prototyping. And with modular design, you can swap out your prototypes very quickly. An important part of modular design is not trying to make the first design perfect. As you can see, these are our junction braces, and on the left, as you can see, is a very early design, just a concept design, not trying to make it perfect, and on the right is a much more refined version, such as the one we have now. Next slide, please. The steps involved in iterative design are: you start with your simple design and you make multiple improvements to your design over time. You observe how a part behaves and then you rethink the problems. Discussing the ideas with others can help. Another important part is redesigning parts that already work to try and make them even better. And then you need to be willing to discard ideas that don't work. Next slide, please. A good example of this is our beacon. Our beacon is designed to sit on top of a cone so that the gripper can release partway, depositing just the cone and keeping a hold of the beacon so it can deposit it somewhere else later. On the left, you can see an early design of the beacon, not trying to make it perfect, just trying to get the concept out there so that we can test it and make it better. On the right is a much more refined version with a larger top and thinner base. Next slide, please. Another thing that was iterated on many times was the material used to connect the top of the beacon to the bottom. Early on in the concept design, we used metal music wire, but the metal music wire was too stiff. So we moved on to using nylon zip ties superglued into the plastic parts. This worked very well in our first two qualifiers and states. However, every once in a while, the zip ties would break. So before Worlds, I decided to try redesigning the beacon to use a different material. This is a good example of redesigning something that already works. I tried using polycarbonate, but the polycarbonate was too stiff, so I moved on to using HDPE hot glued into the beacon. This worked very well and is our current beacon design that worked very well in Worlds. Slide. Another example of iterative design is our breakaway. Our breakaway is a piece on our junction brace designed in case the junction brace gets hit on something. It's designed to protect the junction brace and the servo so that it can break away and then snap back to the original position. These are all of the different designs of the breakaway, ranging from using magnets to springs to magnets and springs. Next slide, please. Another thing that I'm going to be talking about is utilizing tools from past years. If you reuse parts from previous years, you can iterate on them and to make them even better for your current year. We use a base with holonomic drive and two-wheel odometry pods. We were able to use the same basic design as our base from last year and iterate on it to make it even better. Using our CAD system's parametric design system, we were able to input numbers into variables to adjust the size of the base. We were also able to iterate on it to center our odometry pods to make them more precise and swap out our turret bearing to use a more precise bearing instead of our last year's Lazy Susan bearing. These are some examples of how you can utilize tools from past years and iterate on your designs to make your designs even better. Now I'm going to hand it off to Julian to talk about learning from competitions.
Yeah, so I'm sure as we all know, pretty much every competition something goes wrong. We certainly are not immune to that. I think every one of our competitions during Power Play, we had some sort of issue, some worse than others. So being able to learn from those and making sure that you are utilizing those opportunities to improve your robot is very important. Also, in order to have some of those issues not come up, being sure to utilize non-qualification tournaments such as scrimmages or tournaments that qualify for something you've already qualified for. Using those opportunities to test new things is very important and very useful to creating a more robust and reliable robot. And also, since you aren't immune to stuff going wrong in competitions, create systems or have systems in place that allow you to adapt quickly to changing conditions. So when something does go wrong, it's a pretty minor thing that you can learn from and overcome rather than something that will ruin your tournament. So, for example, something going wrong at a tournament, this was at our first qualifier. It impacts our junction brace. Our junction brace was a crucial part of our robot this year. It would lift up and localize the junction, and it also had a beam break sensor in it, which would detect when the junction is within scoring range. And then once that beam break sensor was triggered, then it would initialize a deposit sequence, which would automatically deposit the cone. In this example, we collided with another robot during teleop, and our beam brakes or our junction brakes broke, so we could never trigger the beam brake sensor. So we were essentially a push bot the whole match. We couldn't deliver any cones, and we were just pushing cones into the terminal. After that, we went back to our HQ and we implemented what we called safe modes. So these safe modes allowed us to override a lot of our automation and allow for more manual input. So it's just an example of looking back at what went wrong in tournament and improving upon it to make your robot more reliable. Next is this example of how you can use non-qualifying tournaments. So once again, with the beam brake sensor, it uses an infrared emitter and receiver. It emits infrared light into the receiver, and then when a junction enters that path, then the beam is broken, and then it sends off a signal telling us that the junction's there and we're ready to deposit. We were noticing at many of our qualifying tournaments, however, that the junction would clearly be within the beam break sensor's path, but it would not be sending off a signal. So we were eventually able to identify that external lights, due to the harsher lighting environments from this auditoriums and gyms, was causing extra infrared light to leak into our receiver, which was preventing us from getting the signals. This was very hard for us to replicate at our HQ, at our practice field, because we did not have the same harsh lighting. However, at one of our scrimmages, we went to a scrimmage and we noticed that we were having the same issue. So we were able to utilize that opportunity to design a shroud, which you can see on the right, or a sheath, which prevented excess light from coming in. It was a really easy fix. It took us about 5 minutes. It's just some heat shrink tubing hot glued onto the end of our receiver, but it worked really well, and we probably could not have done that without the scrimmage, or would have been very hard to replicate the same lighting. And finally, this is talking about our flexible code base. So just having, thankfully, one very nice thing about our code base is that we can easily and quickly make changes to it and confidently make changes to it. So, for example, calibration using the amount of light coming into your camera, the exposure, we are able to quickly calibrate that. So once again, if you have harsher lights than at some venues than others, which may increase the amount of white bouncing off your signal sleeve, thankfully we're able to quickly change our exposure to adjust what our camera sees in order to get more reliable, autonomous, and signal reads. And this is implemented on all parts of our robot. Many parts of our code base and our robot are quickly changed. So if we encounter an issue, we can quickly adapt and overcome it and keep going on with the tournament. So that was a lot of speaking. So key takeaways, that if you leave the presentation with anything, this is what we want you to leave with. So build upon your knowledge every season. So make sure that you are doing things that you can utilize in future seasons, and in doing them in a way that you can utilize them in future seasons, and documenting them well so you know how to do it again or how to improve upon it. Design for the ease of testing and prototyping. Make sure that your first designs are very basic and easy to improve and iterate upon. And then after that, go for faster, more complex. Never stop refining and improving. Once you have your base prototype done, the way to get at a world competitive level is to always make sure you are making your robot faster, more efficient, with all your subsystems. And then finally, there's no substitute for real game experience. So go to as many, or take as many opportunities as you can, and also just realize that you can never replicate what actually happens at a tournament, at a practice field, and even a scrimmage. It's hard to, because you have the conditions are different. You're not being judged or refed usually. There's more robots, oftentimes more competitive robots, and also the factor of stress. Stress plays a huge part in driving and performance and communication. So always making sure to utilize those real game experiences as much as you can. And I don't think we have time to take questions, but thank you. And thank you for Technic Box for hosting us.